Record. It's recording. Okay, yeah. So from that assignment, chapter 7 covered kinetic energy and work, and chapter 8 covered potential energy and conservation of energy. 8 was optional, because we'll kind of cover conservation today, and potential energy will be probably next week. It's not much at this level you need to know about potential energy. Um, so yeah, I hope you all read those chapters. At least try to. Did anyone have like any issues in like trying to understand it, or for future reference, would you prefer maybe lighter resources if you do you want more advanced resources on these things? Some feedback. Um, anyone? No, it was all good. You guys were able to absorb the content. Okay. Yeah. So that was what Halliday Resnick Walker. So that's an algebraic physics textbook. A little more on the easier side, you won't really probably need to know calculus-based physics for the for middle school. So yeah, so the textbook is a little more on the simpler side, but it explains things a little more rigorously. So when you're saying you're confused about some things, do you have like an example of something that was confusing or you didn't really fully get? Can actually pull up the textbook too. Um, if you want to like reference a page number. Pull that up. So if you have like a specific page number that you wanted more information on. And I will say, for physics, obviously, the more, right, because there's always like two sides to physics problems, especially numerical ones, which is always like the conceptual thing, like, do you actually get what's going on? And then there's also like just the actual solving of equations, numerically. Okay, cool. I'm signing in to get that access to that. Gotta actually sign in. Where I don't do that. Free canvas. Yeah. Sorry. I'm just trying. Okay, that was my password. I just forgot it. So yeah. I'm just going to. So okay. Before that, everyone was able to access the textbook, right? Page chapter 7. Right. There was no issues in accessing it. I think it should have opened in Drive itself. It's a pretty small one. Yeah. So I'm gonna go there, page 204. Is that 204 in the PDF or 204 uh of the uh book itself, of the PDF? Okay, cool. So I'm in 204. It's 176. I see. Okay. So yeah, so you're referring to when you're saying last page chapter 7, you're referring to the practice problems here? Yeah, okay. Um so let me just okay, yeah. Some of these have required you to do some calculus, which is why probably not all of them, right? So like this gets into some vector stuff, um, which is why largely you won't need it. But remember, we covered vectors, right? Conceptually. When we're doing math with vectors, it's a little more trigonometry to like actually figure out where stuff is. Um, but uh, I don't believe for the first, let me go there. The first set of practice problems shouldn't have required that much computation in that sense, should have been all numeric. Um, yeah, so the first, most of the first ones are all numeric. Um, when you get to like the ones towards the end, those involve the calculus, which, good point. I should have put a disclaimer there. Um, so obviously you wouldn't be required to know that one. So when on the last page, no, you won't get something this complicated. Two reasons for in science both. Two reasons. One, those require a little more math rigor than you will actually need for middle school level science. When you get to high school, you probably will need you will need to know this kind of or these math topics. And then two would be the fact that these are also just longer problems to do. They're not all numeric. And so they're dealing with like different quantities and like these are more like challenge, like almost like Olympiad kind of problems. So you won't largely face those in middle school science. Well, obviously maybe in nationals they'll pull something out. Um, regionals probably not. Um, yeah, they do take a lot longer because again, this is obviously textbook problems, so they're not meant for speed solving. Sensible physics problems will again alert a lot of the time be much more uh, about quick computation, right? So obviously you do need to know your formulas, but it won't be a lot of derived quantities and things like that. It'll just be if you have the concepts. It's a lot more plug and chug than these kinds of problems, which are more testing. Do you actually understand what's going on, and can you apply the like actual math, like calculus and trig, to it? Any other questions about the chapter? I hope that summed it up. More about the content. I know the problems towards the end were a little more advanced. So I'm just going to go over and give you a few more disclaimers. So yeah, so a lot of the derivations you can see were done, or not a lot of them. Some of the derivations were done, especially when we get to like a variable force with work. We're done with calculus, but I don't think um, that should have impeded, right? Yeah. So you still had all the formulas were still given. Um, it's just the derivations that were done with calculus if you wanted to see that, but there. So I'm going to kind of do a quick review of the chapter. Um, yeah, I'm going to do like a quick review of the chapter, just the basic stuff. Um, so first off, what is, oh, sorry, questions? Yeah, we can go over the kinematics assignment too, at the end if you want as well. Um, yeah, really. So let's do a quick review of the chapter. So what is kinetic energy, someone? There's Soham. You can unmute and just throw it out there.
The energy, like when you're doing something.
Energy when you're doing something. Can we get a little bit more specific about doing something? Okay, I see energy, motion energy, or energy of something falling. Yeah. So kinetic, uh, K-I-N-E, right? Same thing as kinematics, it's just prefix meaning moving. Um, doing something, energy of doing something mechanical. Doing something is such a vague term. Uh, Mechanical energy just refers to our sum of potential and kinetic energy. It's just doing something isn't really a term that could be ascribed specifically. If by doing something you mean moving or existing in a force field, then yes. But yeah. So yeah, kinetic energy, motion of movement. Kine, that's our kine, it's our prefix for movement. Um, so let's say I have a roughly, let's just say I have a block of something. What would be my formula to for to if I wanted to find the kinetic energy that it carries? What would be the formula I would use there? 1/2 mv squared. Yep, exactly. So let's break that down. You're halving, right? What is your m in that formula? Mass, right? And v squared, what is your v? Velocity, right? So your kinetic energy of something would be 1/2 its mass times its velocity squared. So that's a very basic formula. They'll love to just give you those quantities directly and ask you to compute. Sometimes there'll be a little more computation to get there, but yeah, they it's a lot of the times it'll just be plugging in numbers into those for science school for that formula. What is work? It's a little more abstract. I want to unmute and go for it. C F over D. Anyone have something else, or just describe what it means in the physical sense? Kind of energy, but I like that definition. It gets into the work energy theorem. But Arjun, for your thing, it's a little wrong. They're not inversely; they're directly proportional. So it would be uh work is equal to force times distance, not force over distance. So yeah, so work our formula for that would be force times distance, right? So just thinking about this, if I have some block or an object and I'm just pushing it along or something, I'm applying a force to it, obviously. And then it's going to travel some distance in the time that I apply the force, right? The product of those two will be how much work I did on the object, right? So keep in mind, whenever you have work, that means a force is doing that work. Um, so Shreya, you were kind of getting into that relationship. What is the relationship between work and kinetic energy? Buddy.
Does work only count if it's like kinetic energy?
Um,
Because
only
like
count if it's
if you're
yeah, but
holding something still, it doesn't count as doing any work.
um, so yeah, that's kind of a common problem. The like a kind of question that they'll use, which is what is not doing work or what is doing work. That more those are really targeting the fact that there's that distance term in the work equation. So um, right, obviously, if you are holding something at rest, like above here, like if I'm just holding my water bottle is not moving right now. So it's no work is being done to the water bottle or on the water bottle. Even though I am applying a force to balance the gravity, there is no, uh, I'm not doing work on it. However, if I were to now, let's say, move the bottle up, now I'm applying a force that's stronger than gravity up, and the bottle is moving through a distance. So that's kind of what that's referring to. Those kinds of problems where you need a distance to for it to be work, right? So if you have a net force of zero and the object was initially just not moving, then there wouldn't be any work done. But that's more about the distance term than movement in general. Does that clarify things? Yeah, okay. Moving something amount of energy. Yeah, yeah, okay. And you're getting closer. So what is so going back uh speaking, what is our equation if we want to apply a force to something? What Newton's second law? What does that tell us? F equals ma, right? And what is the a in that equation, right? The acceleration, right? And what is our physical definition of acceleration? Change in velocity or rate of change in velocity, right? Change in velocity over change in time. Yeah. So it's our rate of change of velocity. Uh, so if we're applying a force to something, let's say the net force is non-zero. What does that mean for our acceleration? If we have a non-zero net force, do we have an acceleration or do we not have an acceleration? We do have an acceleration, right? Bad way of wording that. Um, if we have an acceleration, that means that we have a change in velocity, right? We have at least some velocity that's happening. And so that kind of gets a little closer to the work energy theorem. Soham or Kevin, do you want to take it from there and explain the work energy theorem? Um, one of you two.
Yeah, sure.
Okay.
So the work energy theorem basically says that like when the kinetic energy of something is like all the forces that are acting upon it, like yeah, together. So it's just a sum of all the kinetic, all the forces is the kinetic energy of like the object or whatever. Yeah.
Okay. Yeah. So it's yeah. So kind of so when we're looking at the work being done on an object, we'd first like look at the net force on the object. Um, and so like if the net force is um yeah, so that's what you're referring to with the if sum of forces, right? So if our net force is non-zero, then we're going to be doing some work. It's not exactly the kinetic energy of the object. More specifically, it's the change in kinetic energy. So that's the work energy theorem, which is that the work done is equal to the change in kinetic energy. Um, so yeah, the work done is a change in kinetic energy. That's our big relationship, right? So that kind of makes sense, right? If you have some work being done, then that means you have a force. If you have a force, you have an acceleration. If you have a yeah, if you have an acceleration, that means you have some velocity that's happening, right? I mean, obviously, at an instant, the velocity could be zero. But if you're changing your velocity, then very large parts of that it would be non-zero. Um, and so if you have a change in velocity, then your kinetic energy is changing. Right, so it goes around where your work being done, if I do some work on an object, then that the amount of work that I do on it will be equal to the change in kinetic energy. So we can kind of see that in units from the textbook. What are the units of kinetic energy or energy in general? What are the units of energy?
Joules.
Joules. And what's the unit of work?
Is it still the joule?
Yep. Yes, exactly. Right. It's still joules, right? So our unit for work is joules, our unit for energy is joules, and that just shows that uh, they are related quantities. And so, like in that work energy theorem, the units work out as well. Even if you go back, you can do dimensional analysis on this. Go back down to the base SI units, right? Kilograms, meters per second square, meters squared per second squared, um, which would be your kinetic energy. And then you would have newtons times meters. Newtons is kilograms meters per second squared, right? It all works out. Where a newton meter, force times distance, is the same thing as a mass times a velocity squared. Um, yes, that's a much better way of saying it. Work is a means of transferring energy, is another common definition you'll see. What Kevin's writing there. Yep, exactly. So yes, a force obviously has to be in the direction of our motion. Um, uh, and so, right, because if it's going to change the kinetic energy, it has to obviously work in some distance. I mean, if it has to be in the direction of your kinetic energy in order to change that. Um, yeah, any questions? Soham, Kevin, do you have anything to add about work energy, that chapter 7 in Halliday Resnick Walker?
No, not really.
Just I don't know. I think they like to ask like maybe like one or two questions about like if an object moves or something like that, and then how much like if you do positive, negative, or zero work. So just make sure you memorize those rules or you know like how to think clearly about it. So maybe you can enter on the spot, even if you don't memorize like if you apply it in the same direction or opposite direction, those rules, just make sure you understand what work is. And so you can think about that and get the question right on the spot.
Yeah, was good. I didn't talk a lot about the direction part of work. Real quick, are work and kinetic energy vectors or scalars? Scalars, yeah. Um, so it's not about a direction that you're doing work in. But we do have signs for work. And so that comes down to the direction of motion and where the force is being applied to do the work. Which again, as Kevin said, work has to be applied, force has to be applied along the direction of the motion for there to be a work. And then obviously if it's anti-parallel, or like against the motion of the object, if the force vector is pointing the opposite direction of the velocity vector, then you'd have a negative work being done. Um, yes, it's good there. Any questions you guys have from chapter 7? Um, okay. Um, okay, we're going to move on to next topic then. That was kind of a long review, but um, and these are pretty important topics, so we'll obviously send out an assignment sometime today or tomorrow, so you can get a lot of practice with this. And I'm guarantee you one of these quantities will come up on Saturday. It's just very important. They came up last Saturday, if you remember. We got quite a few kinematics ones, or not last Saturday, 2 Saturdays ago. So these are important in actual sciencable questions as well. So if we're all good with work and energy, or kinetic energy, we'll get to potential later. We can, I guess, get started with momentum and impulse. That's okay with you guys. You guys ready for uh Oh, okay. This will end in 10 minutes again. Usual procedure, just join back once it does. Same meeting link. So yeah, we're going to transition to momentum. Let me share my screen here. It's a little more bare bones. If this works. Yep. Okay. So we already did a review. So let's look at momentum. First off, notation. We always denote momentum with the letter P. I don't know why. I'm sure there's some Latin or Greek explanation for why we use P for momentum. But yes, that is why we use, or that is the letter we use to denote momentum. So if we keep in mind that kinetic energy was our mass times our velocity squared, or 1/2 times our mass times our velocity squared, momentum's a little more simpler. It's just our mass times our velocity. And I usually think this is a little more intuitive of a quantity of why it's useful. I mean, if you're just thinking about it, uh, the mass of something moving, or the mass of an object times how fast it's or its speed or velocity, kind of gives you a good indication of, or it's a good, in semantically, just a descriptor, or it's a good way to describe the motion of an object, right? So that's why in a lot of the older, or like, let's say old, I mean like 1700s, um, like when a lot of this was being like fully developed, they are, especially Newton, he would call this the quantity of motion, and that just referred to m and v. Um, so we're talking about momentum. So let's just take a really basic problem. A 5 kilogram block, and it's moving rightwards at a speed of 3 meters per second. What is the momentum of that block? Hmm. Yeah, I can repeat that. It's a 5 kilogram block, so its mass is 5 kilograms, and it's moving rightwards at 3 meters per second. So as you defined its momentum. 15, right. Our units for momentum would be newtons meters per second. Um, this is one of the annoying ones that doesn't have another name for it. So we just refer to it in Newton meters, not Newton, what am I saying? Kilogram meters per second. Sorry. We just refer to it in its base SI units. So yeah, there's no other like shortened name like joule or anything. It's just kilogram meters per second. Um, so here, use your intuition. Do you guys think the momentum would be a scalar or a vector quantity? I just realized that that's down there. So yeah, it's a vector, as seen. Let's turn on this. Yes, it's a vector. Um, and so I told you in that problem that it was 5 kilograms moving at 3 meters per second to the right. Momentum, it's important, will always keep the direction of the velocity. So whatever direction the velocity is, so whatever direction that the object is moving, that's the direction of its momentum. Um, and so when we have what is mass? Is mass a scalar or a vector? Scalar. And is velocity a vector or scalar? Vector, right. So whenever we're multiplying just a scalar by a vector like this, all that's doing is keeping the quantity a vector. In fact, it's called scalars because it's just scaling the magnitude of this vector. So the momentum is just a scaled uh, velocity vector, and the amount it's bigger or smaller by is the mass. Um, Any questions about the concept of momentum, its units, this mass times velocity? It's a little more simple than kinetic energy. Okay, don't see anything in the chat, so I think we're good to move on. So this brings us to important use for momentum. You might be wondering, well, I mean, it's intuitive, but do we have any mathematical use for momentum? And that we do. So recall, right, we said earlier, Newton's second law was F equals m times A, right? And that is correct. But that's actually a subset or a simplified version. Sorry, we're not there yet. The real Newton's second law is this. Force is the change in momentum over the change in time, or the rate of change of momentum. So much like velocity is a rate of change of position, force would be the rate of change of time. Time? What? Oh, for the meeting? Yeah, the meeting will end in like 3 minutes. Just join back when that happens. Okay. Uh, timer? Time. Is this a question or are you just typing time? Okay. Uh, move on then. Okay. Yeah. So yes, this is how Newton actually put out the second law, and this is the more general definition of Newton's second law. Why does it keep doing that? Kevin or Soham, do you want to go into more depth about this? That's why. Oh, it's off. Okay. Do you want to go into more depth about this and explain why this is the same thing as F equals ma?
Sure. See if I can use like a marker. All right, here. This is kind of bad. So F net equals MA. You can rewrite that as, oh, let me see. F net equals M times change in velocity. Oh, let's go. But you can rewrite it as M times change in velocity over change in time. And if you remember, change in velocity is just VF minus V initial. So we can kind of distribute that in. So basically change in MV or MV final minus MV initial over change in time equals F net. And then we can factor the change out if you kind of think about it. You have M VF minus MVI all over change in time. Remember MV is just momentum, so we have just change in P over change in time. So kind of the important part here is that we kind of factored in the M inside the change symbol or the delta symbol. So we had M times change in V, and notice how we factored that into change in MV over time or change in time. So that's basically where this formula comes from. And then if we had this original formula, we could kind of work backwards to get F equals MA, like what we know as Newton's second law usually. I don't care that.
Yeah, so oh wait, this is about to end, isn't it? All right, it's fine. So can I remove this? I don't know. Anyways,